All right. Good morning, everybody, or afternoon, or evening, or really, I suppose, whenever you watch this. We are on to kind of now the second full week of this EO 8 turn 7 unit. And we got logs coming back. You're going to see definitely a Ren and Stimpy joke here or there. When I say logs, I'm referring to logarithms. And we're going to kind of talk a little bit about why you might sort of need to use them at first. Okay? Brief overview of what we're going to be covering for the rest of the unit in case you're curious. Okay, how logs work. Mostly focused after this on these E and ln concepts and what these sort of things mean and how they work. We're going to talk right now a little bit about why that sort of would be. So I want you to think when looking at this, what do I mean by like an inverse operation? If I ask you to think what's going to go with addition, like what's its inverse operation going to be? Subtraction. If I ask you to think multiplication, what's going to match up with that? Division. If I have something squared and I were to like undo that, what's its inverse operation? Square root. If I had something to the nth power, meaning that could be squared or third or fourth or seventh or whatever number you like, what am I going to do? An nth root, whatever that same number has to apply. Now in this case, if I have something raised to the x, and I'm trying to get that out, I'm going to need logs. This is where they come in. Logs are the inverse to exponentials, all right? I'm going to ask, take 1 minute, but pause the video. I'm going to basically continue in real time. Try and solve all these. Once you're done, come on back and kind of check sort of these answers here. This is probably a good use of the 1.5 times. I'm adding, so I end up subtracting here. X equals 15. 5x equals 20. I'm multiplying, so I'm going to divide both sides by 5. You're going to get x equals 4. I have x squared equals 64. Take a square root of both sides. I'm going to get x equals, technically without any other knowledge, it should be plus or minus 8. X cubed is 27. I'm going to take a cube root of both sides to undo the cubing. I'm going to get x equals 3. If I have 2 to the x equals 64, how do you solve that? What you need for this guy is logarithms in this case. Like, I can't divide by 2. I mean, you could probably reason this out. I think it should be, what, 2 to the 6th is 64? So x is equal to 64, right? What's that going to be? 2, 4, 8, and then 8, 3. Yeah, so it is 6, but the math to get there is a little more convoluted and involved. We're going to work on that here in a second. Basics of how sort of logarithms are, and then just to plant this idea and why we might use these. This left side is an exponential. Okay, I've got 10 to some power equals 10,000, or sorry, 1,000. You could reason that out. It's going to be 3, 10 times 10 times 10. However, all of these different pieces here match up. So I'm currently in this exponential form. I have 10, which is my a, raised to the x, which is my c value, equals b, 1,000, which is my overall value. A is the base, c is the exponent in exponential form, b is the value of that. To rewrite this as a logarithm, it would end up looking like log of this base, in both cases the same. I will say log base 10 of, and then I'm going to put in parentheses, this b value, the value that I actually have, the whole thing that it's worth, equals x. So I went from an exponential, and yes, we know the answer, it's 3, rewrote it in a form, though, where now x is very clearly isolated. That's where you're going to need logarithms in this case. Now, what the heck does this guy actually mean? This means 10 to what power gives me 1,000. That's where that 3 comes in. There's going to be some stuff that you're going to have to use calculators for. There's going to be a few that we're going to ask you to kind of do without. Let's start with a few of those. We can have you try some logs or problems where you're not going to need logs to solve. You could if you knew them. Let's work through a few here because you are going to see a few of these on your test of situations that are going to have exponential equations, but you can do without logs. First up, 2 to the x equals 8. You might need 2 to the x equals 2 cubed. Now, since those bases are the same, I can just kind of ignore the bases, giving me x equals 3. Again, you might have reasoned it out. Try rewriting the base, or like both bases, as the exact same thing, and then we're going to use properties of exponents to go from there. 27 to the x equals 9 to the 2x. I can't make 27 out of 9. So what I'm going to do in this case actually is rewrite both 27 and 9 with 3 as my base. 27 from kind of a couple slides ago is 3 cubed. So I'm going to write 3 cubed, which is the 20, oops, sorry. If I write 3 cubed, not 3 to the x, my right side is now effectively, or this left portion here is 27. I've got 27 on the inside raised to the x power. These are equivalent. If I repeat the same on the right side, instead of 9, I'm going to write 3 squared, but it's raised to the 2x. Oh, goodness. So, if we use some of our properties from last week, how do we deal with these exponents? They're going to get multiplied in. I think it was law 3. This is now going to be 3 to the 3x, because those are going to multiply, equals 3 to the, I have 2 times 2x. There's your 4x. At this point now, I have the exact same base, so I can kind of just ignore the bases, giving me 3x equals 4x. You can subtract a 3x from both sides to get 0 equals 4x minus 3x, or x. Really, this one's only true if you get 0, right? 27 to the 0, what's that going to give you? 1. 2 times 0 is still going to be 0. 9 to the 0 is still going to give you a 1. And then I'm going to write, instead of 16, I'm going to write 2 to the 4th, because that's equivalent, raised to the x. If I use that third log property, multiply this guy in, my right side is going to be 2 to the 4x. My left side is 2 to the 2x plus 3. Since I now have equivalent bases, they're both 2's, I can effectively ignore them, giving me just 2x plus 3 equals 4x. If I subtract the 2x on both sides, that'll give me 3 equals 2x. Divide both sides by 2, I'm going to get x equals 3 halves, or 1.5. I only had to rewrite a single base here, unlike the previous problem where I had to rewrite both bases. Got a little bit of algebra for this guy. You can still solve this without a logarithm. You're going to have to do a little bit more work first. We're trying to get basically this x out of the exponent in this case. If I add a 7 to both sides, that first move is going to cancel these guys out. Add a 7 over here, and you might start to see things take a little more familiar shape. I'm going to get 64. And on my left side, I have 2 to the 2x plus 3. Now we're just basically like that previous question. I need to rewrite 64 as a 2 base. From what we established earlier, that's 2 to the 6th. 2 times 2 times 2 is 8. And if I did another 2 times 2 times 2 is 8. 8 times 8 makes you 64. So I now have 2 to the 2x plus 3 equals 2 to the 6th. Since the bases now match, I have 2 to the something equals 2 to the something. I can kind of ignore them and just go with 2x plus 3 equals 6. If I subtract the 3 from both sides, I get 2x equals 3. And this might start to look a little familiar now. We're going to get x again is 3 halves. Divide both sides by 2. All right, more properties of exponents at play here. I'm going to do two things. I'm going to basically, on the left side, I'm going to do my addition because I'm multiplying things with the same base. I have 5 to the something times 5 to the something. The right side, I'm going to rewrite 25 as 5 squared. So I'm going to go ahead and do the right side first. It's 5 squared raised to the x plus 6. On my left side, boy, my pluses have a little hook today. This is going to be 5 raised to the 3x plus 4. Remember, this is law 1 from last week, those properties of exponents. I'm multiplying things with the same base, add the exponents together. I need to now do property 3 here, which is multiply these in. Be careful. You've got a little distribution going on. Technically, what you're doing is 2 times x plus 6. Why am I getting these hooks on these pluses today? So if I distribute that in, you're going to get a 2x from those parts, and 2 times 6 is going to give you a 12. My whole right side is going to be 5 raised to the 2x plus 12. Left side is going to be 5 still to the 3x plus 4. Because I've normalized the bases, they're the exact same base, I can basically ignore them, giving me 3x plus 4 equals 2x plus 12. I want to rewind and say, like, why I'm allowed to do that again. I basically have this idea. I have 5 to the something equals 5 to the something. When is that true? That's only true if these somethings are equal, right? If I put 5 squared, the only way that works is if this thing is equal to 2. So because I have 5 right here to the something equals 5 to the something, I can set those exponents equal and work my way through the rest of it. I'm going to kind of do two things at once. I'm going to subtract the 4 from both sides, and I'm going to subtract 2x from both sides. The 2x is going to pop over here as a negative. The 4 is going to move over here. That's going to give me basically x equals 8. You can go back and check it if you want. I mean, I couldn't tell you offhand what 25 to the 14th is. It's going to be large. It's going to work, though. More properties of exponents. We've got 2 more of these. We are going to give you a few questions like this on the quiz. Sorry if you hear that noise in the background. One dog is rolling around, and the other is aggressively chewing a bone, so my apologies if that's coming through. I have things on my left side divided. This is law 2, so I'm going to basically subtract these. I'm subtracting like x plus 3 or something. That would get subtracted as well, so the negative would have to distribute into both. Right now, I'm just going to have a 2x minus x, which is going to give me an x, plus 3 is going to be what this whole thing cleans up to. My left side is now 2 the x plus 3. My right side, instead of 4, I'm going to rewrite it as 2 squared. The idea is matching that base raised to the 5th. We're going to do some law 3, so I'm going to take this 5 and multiply it in. I now have 2 to the x plus 3, that's not my best 2, equals 2 to the 10th. I now have 2 to the something equals 2 to the something, so I can ignore the bases and just go with x plus 3 equals 10, and you can likely see what our final value is going to be. X equals 7 after I subtracted 3 from both sides. One more before we start getting to the actual log properties. I'm going to let you think on this one for a moment. What am I going to do? Because I need to rewrite these things with the exact same base. Which base do you think we're going to rewrite things with? Again, keep things kind of normal. Of course, I have coffee around at all times. It's been a little bit of a problem. I've kind of overindulged in caffeine. And then trying to pull back a little bit has led to some caffeine headaches. So that's been my self-quarantine, I guess. I'm actually going to rewrite the 1. And I'm going to write it. It's something that you're probably going to groan a little bit. If I rewrite that as 4 to the 0, does that equal 1? I forget, was it law 7, I want to say, from last week? I don't recall numbers perfectly offhand. I think so. Now I have the exact same base. 4 to the something equals 4 to the something, so I can set those parts equal. 2x plus 3. Kona, are you trying to get on camera? Looks like it. 2x plus 3 is 0. Subtract a 3, so I have 2x is negative 3. Divide both sides by 2. I get x equals negative 3 halves. I'm a bigger fan of fractions. You can turn it into a decimal if you so choose. Okay, the dogs are going a little crazy. Let's see if we can't sneak them in here in frame real quick. So there's Kona. Hey, Combs. Obi, what are you doing, bud? Obes, come here. Yeah, okay, he might not make it for right now. That's okay. We'll have to get him on later. All right, those are basically our sort of 7 how can you solve exponential equations without using logarithms. Not every problem fits this form. There are some that absolutely can, and you could go back after we've covered these skills and solve all 7 of those with properties of logarithms. Totally fine. But you don't need to. All right. Again, big fan of Any of the old school log jokes from Ren and Stimpy? It was a silly, kind of above it, the age grade that, or age level that it was meant for on Nickelodeon when I was growing up. They had a whole commercial series around logs. If you type Ren and Stimpy log, they've got like a little jingle for it and fake commercials, and they brought it back throughout the show constantly. Okay, we've seen this guy already. We already talked about how to basically rewrite these. My apologies. If you're curious what that looks like, you can kind of rewind back to this would be sort of the 6th slide in the first couple minutes there. So let's actually put these things to work, okay? I'm going to walk through a couple different problems here. Found some old slides from last year that have cleaner handwriting a little bit. First step I'm going to do, and this is where the algebra piece of this comes in. I am basically taking the log of both sides. I should probably put some parentheses here. My apologies. I have log of 10 to the x equals log of, oh goodness, 1,000. Basically what I just did is I took log, I want to clarify something here too, and then I put whatever I needed to on the inside. Do you see how right here, this portion, this 10 to the x, this 1,000 are exactly what I had before? My algebra is I took a logarithm of both sides. What happens is there's a property of logs that when you have an exponent going to everything in what's called the argument, this piece of the parentheses here, or where this b value is, if it goes to all of it, you're allowed to bring it down out front and turn it into multiplication. I've also got a little question mark right here because every log has to have a number for its base. Well, you don't see a number right here, and there's a lot of things in math that we see that don't have a number written there. If I have x, what's the exponent? 1. What's the coefficient? Also 1. What number is being added to the end? 0. If I put all of this inside of a root, what type of root is it? A square root. This whole thing right here is the same as just x, or I guess square root of x. We don't write a whole lot of these numbers. If you see a logarithm without a base explicitly written, that number is a 10. I'm going to show you why that comes in handy here. If I now clean this up, there's kind of 2 ways we can approach this. I might cycle back to this guy. By bringing this log down, okay, I've got this x in front now. And some of this should feel familiar from Math 3. I think maybe my slide's a little out of order. I had a slide where there was a properties of logs altogether. It might be at the bottom here. It'll be on the next one. I bring this x down, so I have x now times log base 10, if we don't see a number, of 10. Well, you can kind of do a couple things. I'm going to do some algebra here. This right side, since I don't have a number written, that means log base 10 of 1,000. You could reason out what both of those are, or if they're not always pretty numbers, you can just move your way through it. I'm now trying to get x by itself. So log of 10 is a number. I'll give you a hint. It's 1. It's not really a hint. If I divide both sides by log of whatever this number is, though, x is now completely isolated. Well, how am I coming up with this piece right here? You could reason it out 2 different ways. Both of these have a base 10, which is that small, it's still called the base. Log base 10 of 1,000, that means 10 to what power is 1,000? That gives me a 3. Log base 10 of 10, it means 10 to what power gives me 10? That's a 1. So this is basically 3 over 1. There's also some other ways you can look at this with like change of base formula, which again, you're going to see this. If you looked at the assignment, there is a download that basically has all of those log properties for you. You could also look at this as basically log of, and I can pick whatever base I want. If I take this 10 right here and make it now the base of 1,000, that's using the change of base formula to go from this form back to here. 10 to what power is 1,000? Same deal. Yeah, I guess I don't have them on the slide. My apologies. Here we go. This is what I was referring to. You should see this on a kind of, hey, you learned this stuff from Math 3 sheet. we basically match up the log properties with its exponential property. So right here you see something that's our exponential property 1. When we multiplied things with the same base, we added the exponents. Logs basically flip that. If I have log of and I'm multiplying things on the inside, I split that out into addition of 2 different logs. Repeat that same process with division and subtraction. There's your next thing. We're going to work through plenty of these. Don't worry, we're going to have lots of examples. When I have an exponent raised to an exponent, I end up multiplying. So how do we see that here? When I have this y inside of my log, this argument, it basically brings all of this down in front, so I now have y times log base b of x. We know b to the basically anything to the 0 is 1. So if we flip that around, log base b of 1 means b to what power gives me 1? That has to be a 0. These ones are not so much properties, more as like, hey, yeah, you can reason some of these things out. This last one here, b to the n equals b to the n, isn't super crazy. What I want you to look at for the algebra, though, is this log base b of b to the n. If I have a log base b and a base b right next to each other, they cancel out. So all that I would have left is n equals n. That algebra piece is going to come in pretty handy here, okay? This should be sort of in your homework stuff, so if you want to print this out and use it, absolutely, I would highly recommend that. Let's clean some of these sort of things up, okay? We're going to basically work right now on sort of expanding these using all of these log properties. So this is log of g to the 4th times m. I'm going to do this guy right here first because I have multiplication of 2 pieces. So that's going to split out into addition. Then I'm going to use this guy because that 4 is going to go to this g afterward. Let me show you what I mean. If I reveal that first portion, I'm using this first property right here. Instead of multiplying g to the 4th and m inside of a log, I can split them into 2 separate logs. Now that this guy right here is just log base 10 of g to the 4th, I can use this third property, bring that 4 down out in front. I have 4 log of g plus log of m. I'm always going to say log of, and sometimes you'll hear me explicitly state the base. If there's not a number written, it is a 10. That's one of those numbers of math that we're not going to write very often. What am I going to do for log of p divided by m squared? Which properties on here do you think we're going to use? These two, sort of the second and third ones. If I have division inside of a log, I can split that out into 2 separate logs that are being subtracted by each other. Since any in the numerator are going to be all added together, so that's why this guy's out in front, anything in the denominator is going to get subtracted. So this m squared here, that whole piece goes into its own log separate. If I take this 2 now and bring it down, that's how I'm going to get 2 log m. The converse is true too. I could also move the 2 back up if we need to. We'll give you some where we're going to ask you to expand the logs, and some we're going to ask you to simplify, right, in kind of terms of 1 log. Log of a over bc. Which properties am I going to use? It's basically the same sort of thing as kind of last time. I'm going to really, in a way, do. You could look at it as just this, or it's kind of a combination of both of these. I see division inside of a log, so I subtract the arguments, the piece in the parenthesis. First one, a, any of the numerator ones are all going to be added. Any of the denominator ones, b, c, are going to be subtracted. Now, because these guys right here, this is now log base 10 of b times c. I basically have this first rule within this second piece. Right here, this guy, I shouldn't use blue, pick a different color, matches this setup right here. These numbers can change. None of these have a base written, but it could be a 4, 7, 18, 3.6. I don't care. Nothing changes. I could go back and copy all these slides and put like a log base 6 right here. And the only difference is I'm going to have to go through and write a 6 at every single step for all of these. It won't change anything about how these function. It's just going to make more work. I'm going to get rid of those just to keep going forward so I don't have to add it to the next step. If I now just take this negative and distribute it, you can see that I have minus log b and minus log c. Some of you are going to get good enough at this stuff that you can basically go from here straight to there, and I'm okay with it. Anything in the numerator you're going to see is basically added. This is a positive log right here. Anything that's in the denominator that's being multiplied, both of those guys get subtraction. If you want to do it in sort of this intermediate two-step process, sure, totally fine with me. So here's one that we could do without logs. How would we maybe solve this sort of thing with logarithms? Okay. This is an idea where what I'm going to do now is take the log of both sides. So my left side is going to say log of 10 to the x equals, on the right side, log of 100 to the 2x plus 3. Both of them are going to go inside of a log. Yeah, I don't have parentheses around these, my apologies. The reason this works is the piece inside the green parentheses is the same. I have log of something equals log of something. I've done the same thing algebraically to both sides. Now there's, again, two ways to approach this. You see in this case, I'm taking this x and bringing this down, which, great, okay. I'm allowed to do that. That's sort of that third log property that you'll see. And then I have x times log 10. I no longer have x in the numerator. I just have this piece right here being multiplied. This is log base 10 of 10. Really, this means 10 to what power equals 10. That's a 1. Another thing, too, is that we were showing for that last property. If you have log base 10 of the same base, those pieces cancel out, leaving whatever's left over. It's really 10 to the first, which is why that whole thing is going to go to a 1. You could do it either way. I'm going to continue with the path that we're currently on, though. Repeat the process to the other side. The whole 100 has this exponent 2x plus 3, so he gets brought down out front, being multiplied. Note the parentheses. If I divide both sides by, really I could do log 10 or log 100, it doesn't matter, because I have x's on both sides. I'm just trying to sort of get one of them cleaner, since this guy has a lot more going on with the 2 and the 3. Not so crazy to clean this up, okay? Now, this, I need to figure out what it's worth. We can approach this sort of two ways. You could, in a calculator or even Google, type log 10 divided by log 100. Hit enter. Let's reason out what this one's actually going to be. If I use that second property to go backwards, let me click back to it. If I use, sorry. I can't actually do that, my apologies, because I have division of two logs. I don't have division inside of a log. This first part right here is log base 10 of 10. That means 10 to what power equals 10? We already established that's a 1. Log base 10 of 100 means 10 to what power is 100? It's a 2. So this part in the box right here is just a half. My left side is going to be half x equals 2x plus 3. I'm going to reveal the rest. Not too crazy for the algebra to get there. I took a log of both sides and then used properties of logarithms to continue solving the rest of the stuff from there. All right. Again, some of these, like this left one, could be done without logs. But let's basically do it sort of with a log. The right side, I can't ever rewrite a 16 with a base 3, at least cleanly, so it's definitely going to require logs. Let's take a look. First thing I'm going to do, take the log of both sides. Now, there's multiple ways to approach this. I'm probably, for the purposes of a lot of this online stuff, going to showcase taking log base 10. If we were in person, I would spend a little more time trying to hit the idea of a log base 8. But because of some of the craziness right now, I think it's going to ultimately be easier this way. I take a log base 10, which we don't see that number written there, of both sides. Part of the reasons we do base 10 are it's the normal standard, as well as your calculator can really only do 2 logarithms. If you have a TI-83 or 4 or whatever, it knows log base 10, and it knows something called log base e, which is the natural log. Maybe you remember back from that first slide. We'll get to that guy in the future. You'll notice both of these, I've just taken each side and put it inside of a logarithm. I'm going to bring those exponents down out front. This x is going to pop out front. 2x plus 3 is going to pop out front. And they're multiplied. Divide both sides by log 32. It's the same question, really, except it's now not 10 and 1,000. This piece right here, log of 8 over log of 32, type into a calculator. It's going to come out to 0.6. We could do some interesting ways to kind of like change and address this guy algebraically. Sure, absolutely. Let's come to the right side here. 3 to the x equals 16 to the 2x plus 3. I'm going to take a log of both sides. Again, I'm doing all of these with base 10 because I think ultimately it's going to make things a little bit easier in this form. Just like last time, I'm going to bring both exponents down in front because the x is going to the entire 3. And the 2x plus 3 is going to the entire 16. Oh my goodness, Kona. Kona, hey. It's alright. You gotta calm down right now. Sorry about that. Bring that x down in front. Bring the 2x plus 3 down in front. Again, same process. I'm dividing both sides by log 16. This number is not going to be so pretty. This one isn't. Type log 3 divided by log 16 in your calculator. It's going to clean up. About that. You're going to have to probably do some rounding. Then you basically do the rest of the stuff. Subtract a 0.396x, subtract a 3, keep doing the rest of the algebra. There you go. Let's move on. Now let's think about how I can sort of reverse these processes to solve using sort of reciprocal identities. They're going to undo each other. And I might come up with sort of a clarifying video tomorrow, going through some of these same slides, showing it in a different way. Okay. This now, I'm just going to basically rewrite in exponential form. Okay, and unfortunately, I have to kind of reveal all of this. If you go back to that slide talking about the A, B, and C with the green, red, and blue, this means 5 to what power is 25, or 5 to the x power equals 25. That's where this is coming from. You could probably, if we rewrite 25 as 5 squared, you can clearly identify x as 2. I'm going to do this a different way, though, okay? Let's try this. This one we're going to do 2 different ways. I have a log base 5. What can I do to undo a logarithm? I can exponentiate. I'm going to basically do this. I'm going to make what I call a comically large 5. So this is now 5 raised to the log base 5 of 25. If I raise my right side also to 5, so basically what I have right now is 5 to the log base 5 of 25 equals 5 to the x. Here's what happens. 5 raised to the log base 5, because these numbers are the same, equals 5 to the x. What value does it have to be? 2 is x. That's another way to approach that. Okay, repeat the same process for this guy. This is just taking a logarithm and rewriting it in exponential form. 2 to the negative 16 power equals x is what this means. This was 5 to the x equals 25, which you see we get to even by a different method out of the logarithm. Now for this last guy here, we're going to do a little bit of algebra first. I'm going to add a 14 to both sides, which gives me 2. I'm trying to basically do algebra to get x by itself. I'm going to divide by 12 next to get 1/6. I now have 8 to the x, and anytime I have an x or a variable and an exponent, take the log of both sides to get that out. If I take the log of both sides, I'm at this stage right here. Again, log of 8 to the x, log of 1/6. I'm going to bring the x down in front because it goes to the whole 8. So I have x log 8 equals log of 1/6. Divide both sides by log 8. Oops. You'll need to type this into a calculator. Log of 1/6 divided by log of 8. There's a little bit of rounding here. It's not going to be pretty, right? This numerator means, since we don't see a number, 10 to what power is 1/6? Gross, I don't know. 10 to what power is exactly 8? I don't know. These are things that there's going to be calculator usage for sure with this. I'm going to erase everything from this point down. And I'm going to do it more efficiently than that. To showcase another way to undo this, this is the one that I've sort of referenced. If I have a base 8, I'm intentionally going to take, I'm going to try typing this actually. It might be a little cleaner. Log base 8. And then I'm going to do 8 to the x. I'm taking not now just the log like I originally did, I'm taking the log base 8 of both parts, of both sides. If I do the same thing, oops. I'm going to do sideways fractions because they're way easier to type. This right here means whenever I have that log base 8 and an 8 right to each other, this could be a 10 and a 10, this could be a 12 and a 12, this could be a 13.684 and a 13.684. Those guys will cross cancel, leaving just the exponent. I'm going to get x equals this whole thing. Let's give it a try, see if it lets me copy it nice. There's two ways you can approach this. Okay, I'll just do it right now. You could type log base 8 of 1/6. If you have an 84 plus or newer, I want to say you hit math and then press up. And it should give you something where it literally says like log base. And it will give you a spot where you can literally type 8 and then you can type the 1/6. However, there's something called the change of base formula. I'm going to type it out here to showcase how I'm going to use this. Let's say I'm going to do log of, let's say A of B. That's equal to log, and then I can pick whatever letter I want. Oops. But hold on, I got one more to do. Oh, thank you, Connor. That was a good contribution. Apparently there's a squirrel outside or something. Now this form, let me put the division in here. This is the change of base formula. You'll notice, and I'm going to highlight a few pieces here to basically make this part a little clearer. A, the original base is now the argument. The original argument is the argument of the numerator. And then I introduce this new guy right here. That C can be whatever you want. The reason we do log base 10 so much is if I write this with a 10, let me copy this guy, just for a little bit of ease of some of this. C can be whatever number you want. Remember though, your calculator knows two bases. It knows a 10, and it knows E, which we'll talk about a little more next week. E is a number. I know it's a weird thing to hear me say. If I write this, oh goodness, that's not what I wanted. Let's change that back to a regular old pen. Right? The idea is still the same. Well, what do we have before? In this case, B is 1/6. This is going to be log base 10 of 1/6 divided by log base 10 of 8. And if you rewind the video, what you saw here before was the exact same thing, except we didn't see these 10s. Why is that? We said, if we see a log without a base written, what number is actually there? 10. So that's really what you're doing. That's why this sort of thing works. You can do it either way. I was taught a little more this way, where I would use a log of the exact same base to undo exactly whatever I had there. I think the method is shifted a bit more to just always using log base 10s. Either way works. There's probably going to be the need for some clarification on office hours. Please stop in today or sometime this week. Let's solve a few more. I have logs on both sides, and then here I have an exponential that I'm going to basically work my way to. I can't rewrite 300 as 3 to the something, so it's going to be a little nasty. Well, in a pretty way. Oops, I forgot to. Okay, well, let's pretend that we didn't see that. Let's cover this guy up. And I'm not currently showing it, so I'm going to go in and add it. Right now, if I don't see a number with that log base, what's actually there? 10. What's going to undo a log base 10? If I exponentiate both sides. So what I'm doing now is I'm saying 10 to the log of 2x plus 1 equals 10 to the log of 3x. When I have a 10 raised to a log, remember there's a little 10 right here, those guys cancel out, giving me just the stuff on the inside. 10 raised to the log base 10, those guys cancel out, giving me just the stuff on the inside. You can hopefully handle that math to get x is 1. Let's move to this other guy over here. What am I going to do to get the variable out of the exponent? Take a log of both sides. Again, you can do this with a log base 3 if you wanted. It's going to basically make the process look a little bit differently and have some change of base formula stuff in there, but it's fine. I'm now going to bring this guy down in front because that's one of my properties of logs. So I have 4x minus 1. You'll notice all of it is in parentheses being multiplied by log 3, which is log base 10 of 3. That means 10 to what power is 3? It's not a pretty number. Calculators are going to be essential. Divide both sides by log 3. Again, use a calculator. I have no idea what this is going to be mentally. Now that you've got this, there's going to be some numbers. Okay, let's add our 1, divide both sides by 4. There you go. So what your task for right now is kind of get a start on some of that log review stuff. I'll probably do a shorter video either tomorrow or Wednesday clarifying a few other pieces and maybe running through some of these in a slightly different form. You'll also see a Desmos assignment go live, and there's a bonus sort of sheet that has some of the can you solve these exponential equations without logarithms. That is not a required assignment. You're going to see 2, maybe 3 questions, I want to say, probably on the quiz for this Friday. I believe it's 15 questions total, covering all of this sort of stuff. These things are a little weird. Try something early, make a mistake, let's come to office hours, let's fix it, and kind of work your way through. You'll see answers for this one a little earlier, even though I've listed the due date as Thursday evening for basically all of this. The idea is, here's your work for the week. Be ready for Friday. I was pretty happy with the results of the last one. Kona is just off frame here. Cones. There you go. You're on camera now. You know what that means. She does not speak English very well. I'm trying. It's not really taking. We'll give her a little treat, though, huh? You want a treat, Kona? Okay. There we go. So, you've got your task. We'll let you get to work. This is weird, okay? It's hard to do this sort of stuff online, okay? There's going to be some weirdness with it and multiple ways to approach it. If you find another video that works well for you, great, use that. Since there are multiple ways and you're going to be doing a multiple choice test, I don't really care which method you use as long as it's something that's valid. Please reach out. I hope you're staying safe, healthy, and well. Hopefully you're watching something exciting or playing some fun games or something. Maybe today get out and take a walk for dogs if you got some snow dogs, kind of like I do, at least the big one. And with that, I'm done for now. We'll talk to you all in the future. Look for a short video either tomorrow or Wednesday, kind of going through things in a slightly different manner. Still valid. Have a good day.